Hello. So good evening, and today I will be doing the week 12 of our live sessions for the course of Computational Fluid Dynamics. So there will be one more session after this, which will be held tomorrow. And like today, we will be covering most of the topics that have been covered in the course, and tomorrow we can like do a quick recap of the course and like see if there are any left out topics, and you can also like come with your doubts and we can discuss them and so that you are well prepared for your assessment. So let's start where we left off last session. So, so consider the following statements regarding the stream function vorticity. So we were discussing the different. We started discussing the methods for solving the Navier-Stokes equation itself. So we discussed in the last class about the stream function vorticity approach. So what is this? This is basically an approach where we try to get rid of the pressure term. Why we try to get rid of the pressure term? Because pressure does not have uh, a governing equation of its own. So there is a continuity equation and there are momentum equations, but none of them are explicitly for pressure. So that creates a challenge in our numerical approach. So one way to overcome that is using a stream function vorticity. So what we do there, so as we had discussed in the previous class, we just simply take the curl of the whole equation. Or this can be also described as like you have the Navier-Stokes equation, you take partial derivative with respect to x and partial derivative with respect to y in a separate equation and just subtract the two resulting equations. What you will get will be the stream function vorticity equation for the stream function vorticity. So what you will get is basically will be a transport equation for the vorticity itself. So it will look something like this. So this is basically convection diffusion equation for the vorticity. So zeta is vorticity. And you can see the diffusion coefficient is still your viscosity here. If you consider this to be a transport equation, and let's here no pressure term is there. That was our main objective. So this can be solved very easily. We can find out the vorticity given a guess value for the velocities. So in this approach, what we do, we like take a guess value of the velocity u and v, and then solve for our vorticity. Then after that, we use this particular relation. This comes from the stream function. So, so basically, the Laplacian of the stream function, this will be equal to minus vorticity. So this is simply a Poisson equation if we have already found out vorticity, which we do from this transport equation. So we solve this Poisson equation, we find out psi, and from psi we again find out velocity, which gives an updated estimate of the velocity, and we do this iterative process till we get till we converge to a particular values of the velocity. Okay, so let's start with this with the statements. So the first statement is it is only used in 2D fluids. The thing about this approach is we are using the stream function. So stream function is mainly defined for only the 2D flows. So that restricts this method to a two-dimensional sense. So we will not be able to use this method as elegantly for a three-dimensional sense. So this is restricted to 2D flows. So this statement is correct. So the next statement is it involves a solution of a pressure correction equation. So this is not the case. So we will use this pressure correction equation in the case for simple uh, algorithm and simpler algorithm. Simple and simpler that we will discuss subsequently. Uh, so there we have this pressure correction equation, but in stream function vorticity approach, we do not have any such pressure correction equation. So this is not correct. So the third point is it involves solution of pressure Cauchy equation to obtain pressure field from the velocity. So here we see that we are like doing this iterative method, and we try to find out solution of only u and v. Now what happens when we finally obtain a convert solution for u and v? We also need another variable solution because like our dependent variables are not restricted to velocity, but also we have the pressure. The pressure that we eliminated is also something that we wanted to find. So how we can arrive at that? Uh, so method that we can use is basically it is described in your lectures. So if you take del del x of the x momentum equation and del del y of your y momentum equation and add them up. So if you add them up, what you will arrive after few cancellations with the help of continuity equations. Uh, s- if you use the continuity equation, you will see here the viscosity terms, for example, will disappear. Similarly, the temporal terms will also disappear. Uh, and what you would be left with, what you will be left with is basically an equation like this. So, plus a certain term, I think, like rho, and you can see that this is like this will come from a particular term in the like convective in from the convective terms. So this is rho. So this is density. It was different from the question. So now you can see we already know u and v. So if we know u and v, this part is known. So if this part is known, you can see the form is very same to a Cauchy equation, like something like this. Is equal to some constant or something. Yeah, some. This is basically a constant. So this is something like this. This is a Cauchy equation. So that is what is referred as pressure Cauchy equation. So we do need this pressure Cauchy equation to obtain the pressure field from the velocity. So this statement is also. So 1 and 3 are the correct statements. If you have any questions, you can ask. You can interrupt me anytime and ask the question. All right. So let's go. So now we like move away from the our this uh, stream function and vorticity approach, and we will like start uh, doing some other approaches to incorporate this pressure. So the problem with this is first of all it is only restricted to 2D, and secondly there are like a challenge can be obtaining the boundary conditions as we had seen previously. So the boundary conditions we have for vorticity and stream function does not directly arise from any physical considerations. Instead we like we have a boundary conditions for the velocity and pressure. From there we derive an equivalent boundary conditions for this stream function and vorticity. So if we want to avoid that, we need to solve the pressure and velocity directly from our Navier-Stokes equation. So we will do that, and for that we would also use something called staggered flow. So what a staggered rate does is basically we have our control volumes, and so far in control volumes we had seen that we have some grid points, and around that grid point we have constructed a control volume. So suppose the neighboring grid points are like this. Let's take like a 2D case. So neighboring grid points are like this. So what we have basically arrived at, suppose this is point P, and this is east, west, north, south, and these interfaces, these are E, W, N, and S. So at the interfaces, we calculate the flux, and by the balance of flux, we arrive at the like the governing transport equation in a discretized form. But the variables that we want to solve, the dependent variables, are always for the grid points. Now here we will move away from this concept. We will not on like the grid points will contain the value of pressure. So pressure will be in the grid points, and velocity we would take on the interfacial points, or the like boundary points, like the small letters small e, small s, small w, small l. So here we will take the velocities. So it can be thought of as means uh, the value of the velocity has moved from this to um, the edges of a control volume, or it can also be thought of as if we are creating a separate control volume for velocity. For example, for x velocity, we are creating this control volume where these grid points P and E are actually at the edge, and the small e point is at the center of the control volume and is acting like a grid point. So, due to this approach, this is called a staggered grid approach. So, as if the velocity grids are staggered. What are the advantages of doing this? So one advantage of doing this is that like in control volume in this finite volume approaches we deal with fluxes, and are intrinsically associated with velocities. So if we want to find out flux at the edges, it will be very helpful if the velocity is also found out at the edges. So if the velocities are found out at the edges, we will get an accurate value of fluxes. Also, there is another thing which is like this mentioned in this first point. So, issue of checkerboard oscillations in pressure. So, to understand this, so let us understand one thing first. To understand this, that whatever solution of pressure we get, always we have P plus C. If I add a constant to the pressure, that will also be a solution. So whether if we are solving Navier-Stokes, you would find we have del P del X and we have del P del Y. So these are gradients in pressure. So we do not have any P term. We do not have pressure as it is. We have only gradients in pressure. So what does this do is that it allows for like it does not allow for an absolute value of pressure. You can translate the pressure, add some constant to each and every point, reduce it by some constant, still the results will be same. Why? Because if you simply add P plus C in your del del X, this will be same, still be dP. For the y partial derivative also, it will still be del P del. So even if you add a constant to the pressure, it is still solving the governing equation. It is still giving a satisfactory answer to the governing equations. So let us try to imagine a case where this staggered grid is not there. So let us take a 1D case. So in this 1D case, these are supposed to grid points. Here, bold, and these lines are the interfaces. So let's say this is A, this is B, this is C, this is D. Now, while solving for the this control volume, this particular control volume, the pressure that we will be interested in will be PC minus PP. For C, we will be interested in PB minus P. Again, for A, we will be interested in whatever the point comes this side and B, the difference between these two. So you can see there is a pair form. So differences between B and D are important, but never between B and C. Differences between A and C are important, but never between A and B. So we can definitely have, let's say, like a pressure like, let's say, P pressure here, and we have this P plus C here, and P here, and P plus C here. So these oscillations kind of pattern may take place because the value of pressure at point B is not influencing the value of pressure at point A. So whether it is like increased by a constant C or not will not influence the pressure P. But this creates an inconsistent result. So this is what is referred here uh, when it is said possible checkerboard oscillation. So this looks like a checkerboard basically. One point has some pressure, the next point will have a different pressure. Then the next point will have the will relate to the pressure of the previous point, but again the fourth point will have the other pressure. So like the first point, third point, fifth point, they will have related pressure, and second, fourth, sixth, and so on. The even points will have a different kind of pressure. So so these are the checkerboard oscillations, and this is definitely unphysical and not desirable in our solution. So we do not want that. What helps to reduce this? The staggered grid formation. In this staggered grid, you see the velocity is at the interface. So when you are solving your Navier-Stokes, you are using this particular velocity at E. So in your equation, this PE minus PP, this will be more important. So PE minus PP will be important. So will be PP minus PW for this small w point. So you see PP is so all consecutive pressures are linked to each other, and that is important. That's what we had set to achieve. So that's why this staggered grid geometry is very important when we are solving Navier-Stokes directly from velocity and pressure equations. Okay, so this first point is correct. It circumvents the issue of possible checkerboard oscillations in pressure. It is extensively used for unstructured grading in complex geometries. Now, this is not really about complex geometries. This is simply a numerical procedure that we are doing, even in simpler geometries. So, this is not something that is helpful in complex geometries only. So, this statement is not really true. It is used for all cases where we are solving pressure and velocity simultaneously. It requires extra bookkeeping for the staggered control volumes in addition to the main control volumes. Now, this statement is like true because we would need to understand where the staggered grids are, and we need to solve for the interfacial velocities. So, extra bookkeeping will be definitely be required. While using this grid, velocity is calculated at the main grids while pressure is calculated at the staggered grids. Uh, so this is basically fourth point is basically the opposite. So velocity is actually calculated in staggered grids, whereas at main grids pressure is calculated. So this is opposite. This is also not true. So 1 and 3 here are the correct statements. Okay. Is this understood? This the concept of staggered grid. So
Yes, sir.
we move to the next question. So now we directly come to the questions of simple algorithm. So uh, so this particular question is basically asking to find the correct sequence. So can you tell me what the answer would be? So what do we do in the simple algorithm? So in simple algorithm, first we will guess a pressure value. So after we guess the pressure value, what we would do, we now have our momentum equations, uh, where the pressure would have been important, but since the pressure is guessed, we can use that guess value of pressure to find out velocity. So we use this guess value of pressure to find out velocity. Hmm. But these will also be like approximate values, these because these are calculated using a guess value of pressure. So this is calculated. After that, we use a pressure correction equation. So this is basically arising by the help of continuity, and we use the difference between the actual velocity and what the actual velocity and what this approximate velocity will be to find out this pressure correction equation. So from there we arrive at a corrected velocity. So we arrive at a corrected velocity, and from this pressure correction itself, we will also arrive using this corrected velocity. We will arrive at a corrected pressure, and then we will see whether our equation is satisfied or not. How we will see that? We will see whether the continuity is satisfied or not. So if the continuity is satisfied, we end the iteration there. If the continuity is not satisfied, then we will proceed to the next iteration by using this corrected pressure. So let's see which of these options give us the correct answer. So calculate a velocity field from the guess pressure field. So this is like the first step. So you have a guess pressure field, you have to calculate the velocity. This is the first step. This is the first step. So next we what we have to do, calculate uh, we have to calculate the velocity field. Uh, we have to obtain the corrected velocity field. So calculate velocity field from the solution of correction equation. Correct the pressure using pressure correction. Calculate pressure for next equation. Use the incorrect velocity field to solve pressure correction. Okay. So the second thing that we will do is this one, because we have obtained that this velocity field is the incorrect velocity field. So we'll use this velocity field here to calculate the pressure, solve the pressure correction. So from pressure correction equation, we will first obtain a corrected velocity. So this is corrected velocity, and then we will obtain a corrected pressure. So we will update this pressure for the next iteration. So what is the order? 1, 5, 2, 3, 4. Which option is this? 1, 5, 2, 3, 4. First one. Alright. So let's move to the next question. So this is also regarding simple algorithm. So which of the following statements are correct regarding the simple algorithm? So it is a semi-implicit scheme. It is semi-implicit because of neglecting the effect of pressure correction in the neighboring points on the pressure correction at the correct considered grid points. So I think they are trying to refer to the velocity correction that we neglect. So if you look at the derivation of the simple algorithm, then what you will find is what is generally being done. So uh, you have this uh, u is equal to, like, you have this summation. Uh, so these are neighboring points. U e neighbor. So if this is at an e point, divided by AE plus BE, PP minus P. So this is like a governing equation for the like this is like a simplified version of the momentum equation. So a momentum equation discretization would give this equation. So what are the components of there? So you have UE. So UE is at the E interface. If I am talking from a pressure control volume perspective, then this is U at the E interface. So this is equal to summation of like some coefficients and U of neighbors. So AE is from this U itself, and this is DE. So this is a coefficient for the pressure. So this is basically the like control volume area at this particular interface, the east interface, divided by A. So this DE is basically AE divided by E. So this AE comes from the momentum equation, and this capital AE is the cross-sectional area. So this also actually comes from the momentum equation, basically simply by integrating. Uh, Okay. So here PP and PE, here I have used capital letters because this signifies that they are at the center of the grid points. Because like we take a staggered grid point approach as we had seen previously. So velocities are defined at the interfaces of the control volume, of the finite volume, of the control volumes, and at the grid point the pressure is defined. So this is there, and we find out a approximate velocity from this, uh, and we like take a, so like this is basically this same equation with star on all the terms. So we take the difference of this, and this hyphen is used to denote. So uv uv dash is equal to uv minus uv star. So we have to calculate uv dash, and that we will substitute. So this is equal to uh, these coefficients will be there. So these coefficients will be there. So what we do is basically in the simple algorithm we neglect this term. We neglect this term. And what we do is assume that all the corrections that will arise from this velocity will be taken care by the pressure itself. So, so this I think is being talked about here, neglecting the effect of pressure correction. Instead of that, this will be velocity correction. So we neglect the effect of velocity corrections of the neighbors, neighbors, and all the like the load for uh, accounting for the deviation from the actual solution falls on the pressure correction. So this statement is not correct. Let's go to the next statement. The pressure correction equation is derived by integrating continuity over staggered control volume. So is this correct? So correction equation is definitely derived by integrating a continuity equation, but continuity equation is done over the control volume, not the staggered one, but the like control volume where the pressure is at the midpoint. Because like the sole reason, one of the main reasons for doing this staggered control volume approach was so that our calculation of fluxes becomes easier. And in continuity, we do nothing but like balance of fluxes, and for that we do need the velocities at the interfaces. So, yeah, so like this may be a way to remember this, that the pressure correction equation was not derived by integrating continuity over the staggered control volume, was derived by integrating it over the main control volume where the pressure is at the like pressure is defined at each like central grid points. So this is also not correct. So the third statement is solution is considered to be converged when the source term in the pressure correction equations becomes zero. So if you recall what the pressure correction equation looked like, you will probably so the pressure correction equation after integrating and collecting on the term will look somewhat like this: A A P P P is equal to, like this will be sum of all the neighbors again. So I'm not writing all the terms. This will be sum of all the neighbors plus, and this B is nothing but influx minus outflux. So this is the influx of minus the outflux. So the expression, so the expression for this will be, so this is rho zero is basically previous time step. So Navier stress is definitely a time dependent equation. So we will also have this particular term. So this is basically the generation of mass, kind of. So this will represent the amount of mass which is generated, and like through, if there is any unsteadiness in the flow, then this term will be non-zero. So not only generation but also like accumulation. See, if the outflux is not equal to influx and we have some kind of accumulation of mass which might occur in a compressible flow, then this term will be non-zero. Other than that, what we have this. So notice I am using all small letters here because the velocities are defined at the edges, interfaces, which are denoted by the small letters. So this is east-west. So this is along the x direction. So here, if I put the area, it will be delta y delta z. Plus, similarly, the same things will be there for. let's say the y direction. So rho s us star minus rho n u n star. So this is for the y direction. So this is delta x delta c plus rho b ub. So this is bottom and top d. So u star. So this is delta x delta. So you can see each of these terms, each of these terms are basically mass flux in minus out, and this first term is basically of any accumulation of mass. So this is basically uh, our uh, continuity equation if this B was zero. Hmm. So here solution will be considered converged when the source term in the pressure is zero. So B is the source term, and if this is zero, it means a continuity equation is satisfied, and that we take as a convergence criteria. So this third statement is correct. So if P dash is a solution of pressure correction equation, then P dash plus C is also a solution where C is constant. So that we discussed right now, just like few moments back, that if whatever the solution of pressure is, pressure plus constant will also be a solution. Like provided obviously it satisfies the boundary conditions. Like if there is a pressure mentioned somewhere, then we have to scale it accordingly. And definitely pressure correction term, that is like a difference between two pressures, if that is like added, a constant is added to it, then it does not make any difference to the to this to the solution at all. So definitely P dash plus C is also a solution. Only thing in the global Navier that makes a pressure like pressure term have a unique value is the boundary condition, where we specify the value of pressure at a particular point, and that defines what this value of C will be. If you might think that way, then like whatever the value of this constant, that is specified by the boundary condition. Otherwise, you can definitely move your like translate your pressure with a constant, no problem. So point number 4 is also correct. So 3 and 4 are correct here. So this is good. So next question is, what is the correct form of pressure Poisson equation? So pressure Poisson equation we had discussed like a few moments back. This is basically if you know the velocity, then if you want to find the pressure, what equation you will use. Uh, you can do a small derivation if you want. Hmm. So let's say for the x momentum equation, let's consider a 2D case. So what we are doing now is we are taking the x derivative here, taking y derivative here, and we are adding this to the equations. So here, see, rho is there, and so del x of del t, we can definitely interchange, and we can write this as del t, and here we have del u del x plus del y. So apart from that, here uh, we have, so del u del x will be a term. So we have del u del x whole square, and if we similarly we have u del square u del x plus we will have here also similarly. Okay, so you can see here, like if you pair up this particular term with this term, and like you can take the operator del square del x square out, then you will have del u del x plus del u del y, and from continuity you can assume that to be assumed. So so these two terms would cancel. Similarly, here also in these two terms, you tell del square del y square common, then these two terms will also can cancel out from continue. Here also this term will cancel out, and similarly you can also see other terms like telling the same. So you have this del u del x whole square, del v del y whole square, and you have uh, mm, so I'll come back to that in a moment. So before that, you can also I think cancel out these two terms. So if I take this term and this term, I can take common u del x as an operator. So if I take u del x common, then I have del u del x plus del v del y. So these two terms can go. Similarly, if I from take v del y common, then these two terms can also. So I have a very limited number of terms now. What I will do is in the next step is basically, so I have this del u del x whole square and del v del y whole square. I will try to complete a square term out of this. So I have del u del x because if I know, if I can complete a square, I can eliminate that, right? Because del u del x plus del v del y again will be equal to 0. So for that, I will need 2 del u del x del v del y. And I will subtract the same term. So I will subtract the same term. So minus 2 del u del x del v del y plus whatever is remaining. Del v del x del u del y is remaining. Okay, so that is only there two times. Yeah, so that is there two times. That is now you can see how this comes out. So you have this term, this equal to, you can take 2 common as well. Rho is already common. So from here you can see this is del u del x del v del y minus del u del x minus del v del x del v. So this is this equation, the first equation. Okay. So let's go to the next question. So next question is more hands-on on the simple algorithm. So we have been given momentum equation, displayed as momentum equations for point A and B. Sorry, for point B and C, and we are also given some boundary conditions. So let's just write down the boundary conditions. So UA is 20. So here I have UA, which is equal to 20, and P3 is 10. So P3 is given here. So here we, yes, please. Did someone say any? Okay. So someone is asking for the previous slide, but I don't know when you have said that. Which slide are you referring to? Is this one? So this is just derivation. You can like do it. If, like you should do this hands-on, and I will also like request you to also do the like discretization of the simple algorithm from the momentum equation. Mm. Work it out how it comes out to be. Uh, in the lectures, it is all given very nicely. You can see the lectures and try to do it yourself. So you will have a more clearer understanding of why we are taking some steps. All right. So, so here we can also like you should also notice one thing that the staggered grid is we are following that staggered grid pattern. So, the red lines are basically like if you take the instead of here the convention is different. They are using numbers for the pressure and letters for the velocity. But the red lines you can say are basically like the main control volumes edges. And A, B, these are like the staggered grids, center grid points where the velocities are different. So we have the pressure here and the velocity. Okay. So we have to find out the other points. So P1, P2, and UB and UC. And two equations are given. Uh, uh, so UB is given, UC is given. And we are asked to find out this using simple algorithm. So what we will do, we will first guess P1 star and P2 star. So this we have to guess, right? We have to take a guess and then like follow the steps. So P star and P1 star. Let's also take it to be 10. We can do this any like we can take any value. That's not an issue. So let's take it to be 10. So what is the next step? We have to now find the guess values for the velocities using this pressure guess value. So pressure guess value I have already taken. So what is the velocity guess value? UV star. So this is equal to 10 plus, so P1 minus P2. So this is 0. What about UC star? That is also 5. P2 minus P3, that is also 0. So UV star is 10, UC star is 5. And so these are not velocities, these are basically incorrect velocity fields that we have derived from the pressure. Now what we have to do? We have to find our pressure, like the equation. So pressure correction equation. So pressure correction equation, how we will do? We will use a continuity equation. So what will be the continuity equation? What how it will look like? So we have to basically equate the fluxes, right? We have to equate the fluxes. From there, we have to find out the continuity equation. So here, in the 1D case, this is actually pretty simple. If you take a control volume, whatever the velocity is there, the velocity inlet is there, the velocity inlet exit must be same. So if it is a steady flow, then the velocity in must be equal to velocity out. So it's a steady flow. This is already given. So um, our in our cases, so UA must be equal to UB, which also must be equal to UC. So how we can like find this out in a more like robust way? You can like simply equate the fluxes from both the sides and equate this, and you will find this to be true. So you can also directly use this as a like shortcut for a 1D problem, because 1D problem you do not really have any other way. Whatever the velocity inlet is there, the velocity outlet must be the same. So this actually gives us a shortcut. This actually gives us the accurate values. So like you can use this because like you simply have to find out the actual values by hand. So you can use this, or you can like also simply like take the first control volume, focus on this part, and then you can use this UA star plus DE. DE in this case will be D1. Uh, so for UA case, this will be DA actually. This will be DA. P1 dash minus whatever the pressure is on the other side. Actually, this is UA is given, so this need not to be here. So this thing exactly we will do for UB, not for UA, because UA is already given. So UA is there. For UB, we put this UB star plus DB, UB star plus DB into this P2 dash. So P1 dash minus P2. So dB we know. So what is dB? dB is 2.5. We get it from the momentum equation. So dB is 2.5. UV star we know. UV star is how much? UV star is 10. So this is 10. How much is UA? UA is 20. So dB is 2.5. And we have values for P1 dash minus P2. Similarly, we will do the same thing for UC. UB equal to UC. So UC will be UC star uh, plus DC into P2 dash minus P3 dash equal to uh, UB star plus GB P1 dash minus P2. So UC star we already know, this is 5 plus this we can borrow from here 7.5, and P1 dash minus P2 dash we can like substitute. We can substitute this whole thing with UA actually, because we already saw that this whole expression is equal to UA. Uh, so we can substitute that for UA. Wait, I forgot about the pressure correction. So P2 dash is will be there. However, P3 dash is 0 because we already know P3. So P3 dash is basically correction for 3, which is 0 because there is no correction for 3. So P3 dash is 0. So this is 0. And this will be equal to UA, which is 20. So from here, we can find out P2 dash. What is P2 dash? So 20 minus 5 is 15 divided by 7.5. So this will be 2. And putting this P2 dash here in this equation, we can also find out what is P1 dash. So what is P1 dash? You can see P1 dash will also be 2. P1 dash. So right. Is it 2? So 20 minus 10 is 10 divided by 2.5. 10 by 2.5, yes, gives us 4. Sorry, sorry. This will be 6. This will be 6. You can put it in this equation. You can see, you can put it in this equation. So 6 minus 2, 4. 4 into 2.5 is 10. So 10 plus 10, 20, which satisfies this. So this is correct. So what is the new value for P1? So new value for P1 will be equal to P1 star plus P dash, which is equal to 10 plus 6, which is 16. Similarly for P2, we will have P2 star plus P2 dash, which is equal to 12. So this is the first equation that now we can do one thing. We can try to see whether this like satisfies our continuity equation or not. So what is our UB that we have found out? So UB, if I like put it here, so P1 dash P2 dash is there. So there is actually no means. Yes, P1 dash P2 dash is there. We put it and we will find that UB is 20. And also, like it, since this is a 1D case, you see in the continuity equation there is actually no beta. So b is equal to 0, the source term that we had been discussing previously, that is not there. And since that is not there, you can be assured that if you use the simple algorithm, you need only one iteration to find out your converged solution. So that is very convenient. So what is the solution? So solution here is P1 is 16, P2 is 12, and UB and UC is equal to UA, which is 20. So UB and UC is 20. So UB to UC 20, P1 16, 12. So this first option is the correct one. Okay. All right. So here is a 2D problem. So let us take a short break and like you can try solving this 2D problem, or at least like note down the 2D problem, and then we can we will discuss a little bit and then move to the next questions. Okay. So let's take a short break. So have you tried attempting this question? So here let's see what are the given boundary conditions. Let us write it down here. So let's start. UW is given. UW is given as 60. So this is 60. VS is given as 20. Uh, but there are two more ones. I need to- Anyways, this is a exaggeration. So U here is 60 and V here is 20. Uh, PN is 0. This is 0. PE is given as 12. DN or D6 are given, which is given as an equation as well. So there is also like the equations are given. U E is equal to DE P minus PE, and Vn is equal to dn P minus P. So this is given, and also like guess values are given for us, so that I we don't have to do much of the like accurate guessing by ourselves, and we can arrive at the solution manually quickly. So these guess values are given. So very quickly we can find out uh, what is this UE star and PP star. Hmm. So if we use this, so we will have this UE star as, so B is given as 1. So PP star is 15 minus PE star is PE is given as 12. So PE is given as 12. So we will use that, and PP star is 15. So 15 minus 12, that is 3. So UE star is 3. Uh, what about Vn star? Rest of all the velocities are given. As you can see, Vn and Ue are the only velocities. The rest two velocities are already given. So Vn star. So Vn star. Here Dn is zero point 0.6. So Pp is 15 and Pn is 0. So 15 into zero point 0.6. So that will be that will be 9. Right. That will be 9. So we have the velocities, guessed velocities, and the guessed pressure. We can now proceed to pressure correction equation, which we can arrive by like the means, using the flux equation. So here also it is a steady problem, and take help of this particular equation. It's not this. Yeah, we can take help of this particular expression. Okay, that's it. So mm, so here we will have AP. So let's do one thing. Let's write our uh, like, usual steady state convection diffusion, a steady state continuum equation, and there we can substitute our these values as the mm, instead of velocities we can substitute the values. So we have this x plus del v del y. This is equal to 0. So if we do this double integration here with respect to x and with respect to y, what we would arrive at is uh, we would see a delta y. So delta y and delta x also can we assume? Yeah, we can assume that. That helps us a lot. So here in the u term there will be delta y and v term there will be delta x. So if it is equal to 0, we can uh, like uh, cut it out, cancel it out, and that will be equal to 0. And here we can simply write it as this function plus Vn minus E is equal to 0. So here UE star, so UE will be written as UE star plus DE DE dt dash minus PE dash. These are the pressure correction term. UW is already given, so UW will be as it is. So plus Vn will again be Vn star plus Den, sorry, uh, EP dash EP dash minus En dash minus Vs is as it is because Vs is also given. This is equal to this. So here PE is given, so PE dash will be 0, and PN is given, so PN dash will be 0. Rest of the values is already known to us except the pressure corrections. So what we arrive at is basically so uh, this is UE star, which is 3, plus DE is 1, and EP star, so this is P, EP dash, minus this is 60, this will be there, plus Vn star. Uh, Vn star is equals to 9. This is 0.6 pp dash minus. Please let me know if I am doing any like algebraic BS system. This is it. So from here I can find out the value of this dash. So this is 80 minus 971 minus 368. 68 divided by 1.6. So using this pressure correction value, we can find out the UE as UE star plus BE EP dash. Because anyways, the P dash is 0, so we would not be requiring that. So this is needed. So DE is 1 and this is 3. So this is 4.8, so 72.8 divided by 1.6. You can put that in a calculator. See how much that is. Can you tell me how much that is? So this is 45.5. So you can also find similarly. You can also find this uh, Vn. So Vn will be similarly Vn star plus Dn Pp dash. You can put this also in the calculator. So this is 34.5. This is the correct one. 45.5 and 34.5. Here also we did not have any uh, extra source term that we needed to take care of. If we put these values in the velocity, this will easily be zero. So since there is only one element here, and we chose the values in such a way, and that the solution in one iteration. So let's talk about simpler algorithm. How is simpler algorithm different from the simple algorithm? So far we have been focusing on the simple algorithm. So what is simpler? Simpler is a revised version of the simple algorithm, and uh, so in the statement only you can like see one. It starts with a guess velocity. So this is the correct option. So instead of a guessed pressure value, we first start with a guessed velocity value and use that velocity value to find out a guessed like appropriate guessed pressure value. Hmm. And then again we have to solve the pressure correction equation, and from there again get corrected velocities and use that as a guessed velocity value for the next one. So here you will have, for example, like UP you want to solve. So you will have this UP uh, cap as your guessed uh, value, and you have the usual PP names. So this is what is the difference between the simpler and the simple. So it does not involve any pressure correction equation. So this is not correct because it does require pressure correction equation as well. Uh, so this is not correct. It involves an additional equation for pressure. So that it will do because here we are not using any uh, guess value for pressure, and we have to again use the additional equation for pressure to find out the corrected pressure values. So these two statements are correct. This is the correct. Okay. Next, again, we have to uh, uh, we are given some statements regarding simpler algorithm. So pressure correction equation is used for correcting the velocity field and improving the pressure. Uh, this is the first statement. So here uh, we are actually improving the velocity, and we are not improving the pressure field here. So pressure correction equation here is used to like find the improve corrected pressure and velocity, and we are improving the velocity field for the next input. So here it has got the other way. So this statement is incorrect. So this is improving the velocity field. In simpler, we improve the velocity field from a better guess, from a bad guess to a better guess, field convergence. So if the guessed velocity field happens to be the correct velocity field, then the pressure equation will produce the correct pressure field in one iteration. So if you have the correct velocity value, then the pressure equation will produce correct pressure field in one iteration. So this is true. If you have if our guessed velocity field is true, is correct, then we will get the pressure in one iteration itself. So the simpler algorithm requires greater number of iterations and computational uh, effort than the simple algorithm. Uh, that is also not true because like in simpler we have same amount of steps, so it will not require a greater amount of computational effort. So, mm, so we only have the second option, which is correct. I can't see the time. Yeah. So this is the correct option. Again, another factual question about simpler is solution of pressure correction equation is used to update the pressure for next equation. So it is asked which of one of them is true. So which one of them is true? The solution of the pressure correction equation is used to update pressure for the next iteration. Uh, and what is the next option? Next option is solution pressure correction equation is used to correct the velocity field, but not to update pressure in the next iteration. So, like we just now discussed this in the questions before that, here we are updating the mm, velocities and not the pressure. So we get a guess value of velocity, then we use that to find out and equivalent values for the pressure, and then we use our pressure correction equation to find out the mm, uh, to find out the correct velocity field, and that we can use in the like continuity equation for check to check convergence. Again, we come back come back to a guess value of pressure, guess value of velocity, and then we find out a pressure value from the momentum equations. Then we again jump to the next uh, mm, pressure correction equation. In the pressure correction equation, we correct the velocity field and do not update the pressure for the next iteration. So this is option B is the correct option. So here option B is the correct. So now we have discussed different algorithms. So we have discussed like two algorithms mainly for like solving the Navier-Stokes directly, simpler and simple. And like in case of a CFD packages that we you have like right now. Means we already have some ready-made CFD packages, package softwares, like in form of like different commercial softwares like ANSYS, console, and we can also use like OpenFOAM, and also definitely like you can code by hand. So in all those CFD packages, there are like different parts of the CFD package that are used to solve a given problem. So generally it is divided into three. So one we have uh, pre preprocessor and the main solver, and then we have post process. So before this, we will also have other steps like modeling. We like derive the governing equations, etc. So that modeling part is definitely there before this. But after we already have a set of equation ready, we give it to the preprocessor. What does the preprocessor does? It selects like in preprocessing, you select the method that you use to solve these equations. You will discretize your domain in terms of the method that you are using, whether a finite element, finite volume method, or which like iteration techniques that you are using. That will be decided in the preprocessor. So after you have already set the equations, a solver will basically do the like solve solution. So it will iterate and give you the solution. And after you get the solution, what is the solution? Solution is basically the values of the dependent variables in your grid points, in the different grid points. So after you get that, post processor will give those values in a more presentable format. So it can like interpolate between the grid points to find out the pressure, velocity and pressure at the exact points that you need, and also like can give you like contour plots of the different variables that you are solving. So this is the basic framework of a CFD package. So here are some statements regarding this. So the computational grid is generated using the solver. So computational grid is generated using the preprocessor. It is not generated using the solver. So that is done before you give it to the solver. The discretized equations are solved using a solver. So this is correct. So the solution part is done by the solver. The values of variables at points in between the grid points are calculated using the post processor. So this is also correct. So values of variables in between grid points will always be interpolated from the solution given by the solver by the post processor. So this is correct. Contour plots are generated by the preprocessor. So preprocessor, contour plot, no, preprocessor, we do not really have the solution in hand at that time. So contour plots are definitely not generated by preprocessor. It is generated by the processor. So this is also false. So 2 and 3 are the correct options. It's okay. So user-defined function is needed for which of the following situation? So I like this is more in context of like if you do in most CFD packages it is there in some form or the other. If you specifically are solving using ANSYS Fluent, you will see there are UDFs that you can insert, user defined functions. So these are basically like a script or like in a C written in a C++ type that you can give to the solver, which is in addition to the things that it is already solving. So it is something extra that you also want to incorporate into your solution. So it can be done to introduce a new source term in the governing equation. So this is one purpose that is it is used for. So if you want to have some, let's say, electrical body force or some magnetic body force, so that will have a different kind of a set of governing equation from where maybe you are like deriving that electrical force and you are incorporating that into your Navier-Stokes equation. For that, you need to give a user-defined function. Solving an implicit flow, no, that is a very basic function that a main solver can do. So for this, no user-defined function is needed. So defining temperature-dependent thermophysical properties. Yes, for this also, like for example, your density is actually changing with your temperature. So you want to incorporate that into your governing equations. Let's say you are solving Navier-Stokes as well as you are solving the like energy transport equation for solving the temperature. But you want to link your temperature with the density, such that your density changes when your temperature changes. So if you want to do this kind of things, then or you want to, let's say, change the viscosity also with temperature. So if you want to define this kind of things, then you have to use user-defined inputs to change these properties. So for this also, UDFs are needed. Applying a no-slip boundary condition. So this is also a very basic function. So basically, all the very standard things that we do, uh, uh, like for solving a fluid flow, that you can do in your solver itself. Anything extra that you want to like study, like for example, this kind of effects of temperature dependent effects uh, or some other kind of effects like these electrical effects, or you want to change rheology, real different rheological effects you want to study. So for those things, some user defined inputs will be required. So here, this can be definitely no slip boundary condition is a very standard. So 1 and 3 are the correct option. All right. What else is there? So we have a buoyancy driven flow inside a square cavity, and bottom side is hotter than the other three sides. If the coordinate axes are shown, then the gravity vector should be defined as what? So this is a very like general knowledge kind of a question in this case. This is not much of a CFD net. So if y direction is this, then this is the j cap direction, and g is this direction. So it will be 9.8 j cap. So B will be the correct. It's basically in the direction of the vector. Yes. So with this, we have covered most like the almost all of the course that is like relevant for your assessments. And like tomorrow, we can do some recaps and also like see if there are any lecture portions that we can also cover. Mm. So tomorrow will be the last live session for this course. After that, you will have your assessment. So if there is any question, you can ask. Okay, if there is no question, then I will like end the session here. Thanks for joining.
Thank you, sir.
Thanks.